Alright, so now we're going to take a look at what really ends up being the second chapter and our first really kind of build up in our hierarchical structure discussion. And that is going to be talking a little bit about just some general chemistry. So I know probably right off the bat most of you are kind of thinking, why in the world do we have to talk about chemistry at all in a human anatomy and physiology class? And I'm sure a lot of you are also wishing we didn't have to talk about it because this is usually one of those things that nobody loves. That being said, chemistry is not that bad, and the reason why we have to discuss is a lot of the reactions that are happening in the body and a lot of ones that are necessary for your survival depend upon these different cellular reactions taking place, and those reactions are basic chemistry. Besides that, a lot of different things, especially biochemistry, which is the study of the chemistry of life, ends up being very important to us. So to at least start out here, we're going to look at just some basic chemistry, so your general atomic structure and some of the main bonding characteristics. So first to study a little bit about chemistry is the study of matter. So what is matter? And I could do that bad what's a matter joke, but we'll stay away from that one. Matter is anything that takes up space, and your book says, and has weight. And it is composed of elements. Technically, I don't think this definition is 100% correct. It has weight if it's in a gravitational field, such as on the planet. So yeah, we would have weight here. But if I sent you up in space, you would not have weight, but you would still be made up of matter because you take up space. So not the best definition in the world. So elements, these are the different types of matter. And an atom is the smallest amount of any element that is going to have the characteristics or properties of that element. And we're going to see that there is 92 naturally occurring elements. Those are what are on the periodic table, which I can show you if you really want to see it, but we're not going to worry about that too much. And some elements we need at large amounts in the body, so things like carbon, and some we need just a little bit of, so things like iron or some of those other really trace elements. So what are the three parts of an atom? So what we have over on the side here is a little kind of generalized picture or cartoon version of an atom. An atom is made up of three different types of subatomic particles. We have a proton, a neutron, and an electron. So protons are in the nucleus, and usually when we start talking about atomic weights and things like that, these are count as 1 on these different weights here. And protons, they start with PRO, start with P, positive charge to those. Neutrons are also in the nucleus. They count as 1 on the atomic weight, and they do not actually have any charge. So neutrons, neutral, they kind of both look a lot alike. Easy to remember that one. The last one is the electrons. These are orbiting around that nucleus. They do not have any weight to them, and they have an equal negative charge to that proton. And what we're going to see is in any particular atom, the number of protons and electrons are going to be equal. So any atom in nature is going to have a neutral charge overall because it has equal numbers of protons and electrons. So to kind of give you an example here, a hydrogen has 1 proton, 1 electron, as you can see here. Here is that 1 proton, here's the 1 electron orbiting. You can kind of see it shown here. Where carbon, 6 protons, in this case here, this version of it, 6 neutrons and 6 electrons orbiting around. We're going to see on certain elements like carbon, you might have 6 neutrons. Sometimes you can have more than that, and we'll talk about these in a little bit, but those are what we call isotopes. So the atomic number, which would be the thing that everything's organized in the periodic table. So if you start looking at a periodic table, which is Appendix A, at least in the book that we use, that is hydrogen would be number 1. It has 1 proton. Helium is number 2. It has 2 protons. That is its atomic number. The atomic mass or weight is pretty much the adding up of the number of protons and the number of neutrons. And you might ask, well, if we have protons, neutrons, and electrons, why don't we count the electrons in the weight? And the best analogy I can give you for this one is, let's say you're a zookeeper and you're getting ready to weigh an elephant. And the elephant's up on the scale, you're looking at it, and while the elephant's on the scale, a fly lands on the elephant. Did that really affect the weight of the elephant? And in all truthfulness, yes, but when we're really looking at the relative weight difference that is going to be, it'd be almost insignificant. And this is really what happens with electrons. Electrons are so what we call infinitesimally small that the weight of them might be like 0.000000001 added on to the weight of those protons and neutrons added together. So it's such a small amount, it's insignificant in the overall weight. And as we said, the number of neutrons in anyone can change, and therefore that atomic weight or mass can change. An isotope is what we refer to as the same element with different number of neutrons, or the same element has a particular atomic number, but its atomic weight can change. Those different forms would be isotopes. And an ion is what we call it when we can lose or gain electrons, and we'll see that ends up becoming important to us when we get into bonding. A cation is a positive ion, and an anion is a negative ion. So an isotope, like I said, is these different versions of the same element. So in carbon-12, it's stable. It has 6 protons, 6 electrons, and 6 neutrons. Carbon-13 is 6 protons, 6 electrons, 7 neutrons. And carbon-14 is actually not a stable element. It has, again, 6 and 6 of protons and electrons, but it has 8 neutrons. And a lot of times we talk about radioactive isotopes. These are going to be the ones that release some particles because they're not stable. So radioactive isotopes a lot of times break down and will emit radiation, emit particles. And the reason why I bring up radioactive isotopes is just for the simple fact that a lot of different tests that you'll do, so like thyroid activity, looking at the activity of thyroid, one of the things that the thyroid needs is iodine. One of the ways to study this is to put radioactive iodine in the body where the thyroid will take it up. There are certain radioactive isotopes that we use for different tests within the body. So that's why I like to introduce this idea, just because you will at one point or another a lot of times have to be familiar with radioactive isotopes. Like I said, a radioactive isotope, you can look at the thyroid gland and see that it's taking it up correctly. So like they said, they use radioactive iodine, and if it gets taken up correctly, that shows us that the thyroid is healthy. If it doesn't take up the iodine, it means something's wrong. It may mean cancer, it may not, but it definitely means the thyroid isn't working correctly. So that kind of gets you through at least your general subatomic particles, so protons, neutrons, and electrons. But really when it comes down to it, we're not made up of one particular element. We're a combination of a number of different elements, and therefore to put us together, we need more than just one element. We need to start being able to put elements together to make more complex structures. And this is where we get into molecules and compounds. So a molecule, very simply, is a particle that happens when you take two or more atoms and put them together. They can be from the same element, they can be from different elements. It doesn't really matter. O2 is a molecule. H2O would also be a molecule. A compound is the more specific definition of a molecule, really. It's a particle that's formed when you get 2 or more atoms of different elements combining. So again, that O2 would not be a compound, it would be a molecule, but H2O would be both a compound and a molecule. And once we kind of start putting these things together, we can start writing these out as molecular formulas, which you can see down here, H2, 2 hydrogens together, C6H12O6, that's glucose, 6 carbons, 12 hydrogens, 6 oxygens. And what these really show you is they show you the particular element and how many atoms of that element is in this particular molecule. Not showing you how they're bonded together, how they're hooked together whatsoever. Really not showing you anything about the structure. But it does tell you what's there. So how do we put these atoms together to form a molecule? So how do atoms bond? Really what we need is it's going to be dependent upon these electrons. So we get attractive forces between electrons. And we're going to see that there is 2 main types of bonds that we're going to worry about. We're going to talk about ionic as well as covalent bonds. And how this all really kind of works out is you have different energy levels in the atom. So we have, and this is true about the first 18 elements, which is really the main elements that we're made up of. So this works pretty well. The rules are still similar after that, but they break down a little bit. But what we have is we have these what they call energy levels or energy shells, and they're going to hold a particular number of electrons. So the first one that is shown here holds 2 electrons maximum. So hydrogen, there would only be 1 electron in this. Helium, it would fill this one. And what we're going to see as a general rule is that for these atoms to be completely stable, they like their outermost electron shell to be filled. So in the case here, this would be helium. It would be a completely happy, self-fulfilled atom. It does not want to bond with anything because it already has 2 electrons in its outermost shell. Another rule is that the innermost shells have to be filled before you start putting electrons in the outermost shells. So it's one of those, you couldn't take hydrogen, which only has 1, and put 1 electron in the second energy level. It doesn't work that way. It has to put it in the first one first. Helium puts the second one in there. Lithium will start going to the next energy shell. So the second energy shell, as we're going to see here, can hold up to 8. So this gets us up to 10 electrons total. So you can see 2 in the first one, 8 in the next one. Again, it's going to fill the first shell first, and then anything after that, you're going to start filling the outer shell next. And finally, the third energy level can hold 8 as well. It's stable when it gets 8 there. And again, these things are looking to fill their outermost shells through bonding or through giving up or taking on an electron. So ionic bonding is what happens when it's generally the ones on the periodic table that either have 1 too many, so like lithium. It has a 3, or showing you sodium here. Sodium has 11, so you got 2 in the innermost shell, as you can see here. 8 on the next shell, that's happy, but you have 1 extra one on the outermost shell. It doesn't like that. It's kind of like, oh, I was so close to being happy, but I have this 1 extra one. So a lot of times what it wants to do is get rid of that. Well, if it gets rid of that, it loses an electron. It now has 11 positive charges, only 10 negative charges, so it can become a positive ion. Chlorine's kind of the opposite here. It has 2 in the innermost shell, 8 on the next one, and because it is 17, it has 7 on the last one, so it's 1 short. A lot of times it wants to take on 1 more. So if this one gives it up and this one takes it on, we're going to see now chlorine is going to bring on a negative charge because it has 18 negatives and only 17 positives. So what we end up with is a positive charge on the sodium and a negative charge on the chlorine. What happens then is they look at one another and they say, I never really noticed it before, but I find you strangely attractive because, according to Paula Abdul and MC Scatcat here, opposites attract. So the positive and the negative charge will be attracted to one another, and it's this electrochemical charge, attraction of charges, that is going to cause an ionic bond to form. So sodium chloride forms by an ionic bond. You lose an electron over to the chlorine, it becomes negatively charged. The fact that the sodium lost an electron means it's positively charged. These electrical charges, opposite charges, are attracted to one another, and these are bound together. Covalent bonding, on the other hand, is a little bit different. This is going to be a sharing of electrons. So what's going to be happening here, instead of one giving it up and another one taking it, they'll just both kind of go, well, how would I let my electron go around you for a little bit, and you let your electron go around me, and it'll be like we both actually have 2. And we're going to see that's really what kind of happens with a covalent bond. So you can kind of see here, oxygen would be an 8, so it'd have 2 on the innermost shell and 6 on the outermost shell. Hydrogen each has 1 and 1. Hydrogen wants 2 on its outermost shell, and oxygen is going to want an 8. So what happens with these bonds right here, you get a single bond where oxygen is contributing 1 electron, hydrogen is contributing the other. Same thing here. So when it really comes down to it, oxygen is happy because it has 8 at some point or another, always zipping around it, and each of the hydrogens are happy because they are always have 2 going around those. That is a covalent bond. You can do this with more than 1 pair of electrons, though. So like carbon dioxide, 1 carbon, 2 oxygens. Carbon needs 4 because it's a 6, so 2 in the innermost shell, 4 on the next. And on this one, you can kind of see here, 6 on the outermost shell here. This innermost shell is already filled. Same thing over on this one over here. So what happens, they're going to share 2 pairs of electrons, and we get what's called a double bond. And you can do this all the way up to, like with nitrogen, sharing 3 pairs. Quadruple bonding doesn't happen because it's kind of like when you play Twister. You can only get so close to somebody else before you start repelling them or knocking them over. And the same thing that happens here. As these share more and more electrons, their nuclei have to get closer and closer together. And at some point, the positive charges in those nucleuses will start forcing that apart. So it can't do it with quadruple bonding. So just to kind of remind you, ionic bonding is a loss or gain of electrons. You're going to end up with ions. With covalent bonding, it's going to be sharing of electrons. A lot of times this is going to end up making organic molecules, especially when we're talking about a lot of carbon in these things. And we're going to see a lot of these different organic molecules when we discuss a little bit more of the biochemistry at another point. One of the things that can happen with certain types of covalent bonds, so remember how we were seeing how this is a little bit tweaked in one direction here. Oxygen being such a larger one than hydrogen, a larger atom. It's kind of like with a larger planet, you have heavier gravity. And because of this, the oxygen is going to hold those electrons a little closer to it than they are going to be the hydrogen. So what you end up with is you end up with a partial positive charge on these hydrogen atoms of water and a partial negative charge on the oxygen. And what you can get is you can get these water molecules interacting with one another through these little bit weaker bonds called hydrogen bonds. And this is why if you were to pour a glass of water and you put a little bit too much in there and you get that little bubble of the water going over the surface of the cup, that surface tension, it is due to this weaker interaction of hydrogen bonding between all water molecules. That's why water molecules are attracted to one another. If you did that same thing with vodka, which has a nonpolar molecule in it, so ethanol, it will not do that same thing. You cannot get it to bubble over the surface. And again, this in water especially is really vital to our life. Again, it shows you the partial positive, partial negative. So the negative here interacts with the positive and you get this whole network of water molecules.